Hey class, and welcome back. If you remember, just in class last time, this morning for me, but who knows when you're watching this, we left off just introducing this chapter 2, section 3 idea of momentum and angular momentum, right? And so I want to kind of build off of where we left off in class. So our first question, which was really not the best way to ask the question, but was, does a moving bumper car carry a force with it as it moves along? And we said, no, it doesn't. The physical quantity that it carries with it to describe sort of the amount of inertia it has while moving, right? So it's a combination of its inertia and its motion together. We call that physical quantity momentum, and it's a conserved vector quantity, which means that if you have an isolated system, one that's free of any external forces, then the total momentum in your system will not be created or destroyed. Instead, it will only be transferred between different objects. So again, if you have two balls here, if one's moving in and it hits the other one, the total momentum that the two balls have together will remain constant provided that there's no outside influence. And this is true whether they're moving towards each other, moving in the same direction, or if one's stationary and the other one hits it. All cases, you still have conservation of momentum if there's no net outside forces. But if I take the ball and throw it at me, it sort of just bounces off, losing its momentum. And that's because for me, rooted on the ground, I have outside forces that make it a non-isolated system. And as we learned in lab, we quantify momentum as being equal to the mass multiplied by the linear velocity of our object. And we use the letter P to represent momentum. So momentum equals P times M times V. So let's do an example with this idea of having conserved momentum. So I don't know about you, if you've ever fired a firearm of any kind, you've probably felt the recoil or the kickback of the gun that you were using. So I want to do an example with this. Let's imagine that we set up a safe experiment in which you have kind of a hanging gun that's sort of being held loosely, and you pull the trigger and the bullet comes shooting out as a result of the ignition of the gunpowder. And as a result of the kickback that we're familiar with, that gun will move backwards as the bullet goes shooting out. So you have the gun, you have the bullet, you pull the trigger, and as the bullet shoots away really fast, the gun will move backwards. My question to you all is, how fast, at what velocity would the gun recoil? So let's say that the gun is 3 kilograms in mass, the bullet is 50 grams or 0.05 kilograms, and the bullet's exit velocity is 300 meters per second. How fast would the gun kick back? Well, to do this, we need to do conservation of momentum. We need to consider this idea of what does the momentum look like before and after the ignition of the bullet. We're assuming that this is an isolated system. So the first question is, what is our initial momentum? Well, if the gun is there stationary and the bullet is inside the gun also stationary, my initial momentum of the bullet is 0. So here's my initial momentum, and that's going to be equal to my final momentum, which is a combination of the momentum of the bullet as it comes out of the gun and the momentum of the gun as it recoils. All right, so we know that momentum is equal to mass times velocity. So that means mass times velocity for the bullet plus mass times velocity for the gun, again after the trigger has been pulled, is equal to 0, our total initial momentum. So doing some algebra, if I add this to the, or excuse me, subtract this from both sides, I move my mass of the gun and velocity of the gun over here with a negative sign, and then I can start to solve. So if I plug in, here's the mass of the bullet times the velocity of the bullet equals the mass of the gun times the velocity of the gun, but in the opposite direction. So then, solving again, I just take the momentum of the bullet, divide it by negative mass of the gun, and we should find that the gun would recoil at a box-worthy 5 meters per second in the opposite direction of the bullet. That's what the minus sign means. So it'd kick back at 5 meters per second. Doesn't seem that fast, but its acceleration is very high. It happens very rapidly. So I had a friend one time learning to hunt with his wife and his wife's family, wasn't thinking about his physics and didn't properly support that kickback and came to work the next day, unfortunately, with a big black eye as a result of the scope kicking back with the gun into his face. It didn't feel good, but he survived. So, how does an object experience a change in momentum? If you have a isolated system, momentum doesn't change, right? It's conserved for the system. But how do something get momentum in the first place? If I want to take this ball and give it momentum, what do I need to do? Well, I need to apply a force to it, right? If I throw it, if I give it a force, yeah, boom, it'll gain momentum, right? Now it's flying across the room. So you apply a force, and that force has to be applied over a certain period of time. And this is actually another physical quantity that we care about and use a lot in physics. It's known as impulse. So the impulse of an object, or really of a force on an object, might be a better way to do it, is equal to two different things. You can quantify it two ways. It's equal to the change in momentum, which is also equal to the force multiplied by the time. So you can see here, impulse equals change in momentum, which also equals force multiplied by time. So here you see a ball's moving in one direction, it gets kicked off in a different direction. This guy's foot applied a force to it over some period of time, giving it a change in its momentum. And you could actually calculate, based on the velocities and the masses, what the change in momentum is, which would allow you to figure out what the impulse is, which would let you figure out the force if you knew the amount of time. And we're going to do that in an example problem here in a minute. So thinking back to our example of bumper cars colliding together, they transfer momentum via an impulse. So anytime they collide, they're going to change momentum, which means they apply a force to one another over some period of time, and we call this, again, impulse. So impulse is change in momentum. It's also force times time. Both of these are accurate definitions of what impulse is. It's a way in which motion is changed for an object. Again, if this happens between the bumper cars in an isolated system, what that really means is there's no overall net change in momentum. There's a force times time. So one ball might lose momentum while the other ball gains the momentum, but they're just exchanging it via an impulse. So again, a lighter car will have a larger change in velocity because it has less mass, so it needs more change in velocity to experience the same impulse. So here's the example that I said, and I actually want you to pause the video and try this one out. So you take a ball and you just throw it straight at a wall. Right? So you throw the ball at some wall, all right? My whiteboard if I want to. It's moving at 30 meters per second towards the wall, bounces back at 20 meters per second. So here's kind of a picture to show you what it looks like. I want you to tell me what is the impulse that results from this collision with the ball and the wall. Okay, so what's the impulse of the collision? The impulse that results from the force exerted by the wall. And if you were to look at a slow-mo video and observe that this collision only lasted for 0.01 seconds, what would the average horizontal force be? So what would the force be during that time if that's the duration, the amount of time that the impulse happened? So some hints for you. Keep in mind, impulse equals change in momentum and impulse equals force times time. So I want you to start by finding the change in momentum, then try to find the force once you know the impulse. All right, so hopefully you paused it and tried it out. I really want you to give it a go. If you haven't, go back and do it. So we want to start by finding impulse, right? And impulse, as I mentioned, equals change in momentum, or it equals force times time. So since we know about mass and we know about velocity, I'm going to start by using the definition that impulse equals change in momentum. So impulse is going to equal my final momentum minus my initial momentum. My final momentum is my mass times my final velocity. So since it comes back, let's flip back real quick. If we look in our picture, our final velocity is in what I'm calling the positive direction, whereas my initial velocity is in what I'm calling the negative direction, okay? So my mass, 0.4 kilograms, times my final velocity is going to give me a positive 0.4 times 20, that's a positive 8 kilograms times meters per second. And then my initial momentum is going to be 0.4 times negative 30 meters per second because it's going in the negative direction. And so that should give me a negative 12 kilograms times meters per second, but since it's minus a negative, it becomes a positive. So I have 8 plus 12 kilograms per times meters per second, and so my total impulse is a box worthy, look at that, 20 kilograms times meters per second. So for part B of this question here, which is labeled oddly part A again, so I apologize for that, that's part B. For part B, we want to find the average force. So impulse also equals force times time. We now know the impulse, so if we want to find the force, we just take the impulse and divide it by the time. So force is impulse divided by time. Our impulse is 20 kilograms times meters per second. Our time is 10 milliseconds, or 0.01 seconds. And so our force comes out to be a box-worthy 2,000 newtons. All right, so that's the idea of impulse. And you can see it can equal change in momentum, while it also equals force times time. And you can use those two ideas powerfully together to learn a lot about the world. And in fact, impulse and momentum is a very common topic people use in their final projects. So you can think about that idea, especially if you have access to kind of slow motion video capture. So that's kind of the first half of the second section. The second half, we want to just take those same ideas and apply it to rotational motion. So do things that are spinning, like bumper cars, do they carry with them a torque somehow? And again, the answer we talked about in class is no, that's weird and silly, right? What they carry with them is a form of rotational motion, right? Rotational motion with rotational inertia, or what we define as angular momentum. So angular momentum, again, is a conserved vector quantity, something that we're going to do and talk about in class on Monday a little bit. I mean we're going to use some demonstrations. So angular momentum is a vector quantity that can neither be created nor destroyed. It's only transferred provided that you have an isolated system. And so angular momentum, again, as we defined in class, is going to be equal to rotational mass multiplied by angular velocity. Now notice, again, we're running out of letters, so for angular momentum, we use the capital letter L to define angular momentum. So as I mentioned earlier, right, if you have a system that's free of any net external torques or outside torques, then angular momentum will be consistent or remain constant. So a cool application of this is actually orbits. The Earth is in orbit around the sun. It's a system that's free of any net external torques, and so our orbit once a year around the sun stays very consistent because there's no external torques. There's no outside meteorites or anything crashing into us, at least not significant numbers of them with very much angular momentum, so it stays very, very consistent. And the same is true about the angular momentum of the Earth as it spins around its axis. One day remains 24 hours because it's in an isolated system. We have a certain amount of angular momentum, and that is remaining constant because we're free of any significant net external torques. So rotational mass now, it's a little different than normal mass, right? So for linear momentum, to exchange momentum, you need to usually collide different objects because the mass of an object doesn't typically change very readily or easily. That's different for rotational mass. My rotational mass with my arms out and arms in, those are different. I can change my rotational mass quite easily, and I'm going to do some demonstrations of this for you guys on Monday. But since rotational mass can change, it's actually easier to change your angular momentum. And again, you can think very readily of figure skaters. As they are spinning with their arms out, they have one speed. As they bring their arms in, they start spinning much more rapidly because they're changing their rotational mass while keeping the overall angular momentum constant since it's an isolated system. And so if your rotational mass goes down, your angular velocity must go up to keep it at a consistent value. And so this explains the answer we had to our introductory question at the beginning of this section during our last class. When you move towards the center of a merry-go-round, you start to spin faster because of conservation of angular momentum. The last thing I want to define in this video for you all is the idea of angular impulse. So just like with linear momentum, if you want to change the linear momentum, you need a force applied over some time. to change the angular momentum of something, you must have a torque applied over some time, and that torque being applied over some time that results in a change in angular momentum, we call that angular impulse. And it's very, very similar to linear impulse, as we've talked about already. So it's a mechanism by which two objects can exchange their angular momentum. So again, just to kind of use the bumper car analogy to wrap up this section and really to wrap up chapter 2 altogether, here's two bumper cars. As they collide with one another, if we want to just think about angular momentum, if you're in the blue car here, the purple car is going to apply a force to your car at some lever arm distance away from your central axis, right? Your axis of rotation, your center of mass. So there'll be a torque, because torque is force times lever arm. And that torque applied over some period of time causes you to experience a change in your angular momentum. And so that's why you will begin to rotate. You will gain some of the angular momentum from that purple car as its rotation slows down as it slams into you. So it's going to bring that clockwise, counterclockwise angular momentum into your car, hitting your car, causing you to rotate and slowing its rotation. So that's the idea of momentum and angular momentum. We'll do some fun examples with this on Monday, but that actually wraps up chapter 2. So let me know if you guys have any questions. And other than that, have a box-worthy day and a box-worthy weekend.